All right, good morning. Welcome to the start of week 6. I'm sorry to interrupt the Seinfeld episode for class, but 2 announcements. 1, Problem Set 4 did go out on Friday, and please take your teaching fellow's advice to begin these things early. It rather breaks our heart to see some of you guys in the labs on Friday nights and Saturday nights and Sunday afternoons, and frankly, these things are designed to be at least somewhat, if not very fun, and I am sure they are not somewhat or very fun when you are working down to the wire. So at least try to do yourself the service of enjoying these things by diving in a bit earlier. So thanks to Microsoft and that fellow from Halo 3, we've been given a copy of Office Ultimate 2007 to raffle off to you all. So I think what we'll do is this. If you are interested in walking home with a copy for Windows of Office Ultimate 2007, which apparently includes Word 2007, Excel, PowerPoint, Office, Publisher, Accounting Express, Access, Groove, OneNote, and InfoPath. Go ahead and send an email to CS50 plus raffle at FAS by Wednesday morning's lecture. And just to make things interesting, what I will do before your very eyes is write a program that pseudo-randomly chooses the winner out of those who apply. So bear that in mind if you're at all interested. Any questions on anything related to CS50? Anything at all? No? All right. Well, quiz 1 is coming up already. This is the second of 3 quizzes, the details for which are in today's handout. Do bear that in mind. That's 1 week from this Wednesday. So let's take a look at one other function in CS50's library, and we'll see how this applies to some of the stuff we're doing today. So getString, recall, is the function that is used by getInt and getDouble and getFloat, pretty much everything else, because it's really the most important one to actually get that string of text from the user. So let's take a look at how we've actually implemented this and wherein lies some of the interesting details. What function have we been using thus far built into C to get input from the user besides using CS50's getString? We saw this last week. What's this function? So you can use scanf. And the catch with scanf, though, is that even though you can get formatted input from the user, that's the F in scanf, even though you can get formatted input, and by that I mean a string or an int or a float, and let scanf sort of do the busy work of converting that actually to the primitive you want, the catch is that you have to provide scanf not only with that format string, but what else? So you need to pass it a buffer. And a buffer is, what's another way of describing a buffer? Yeah, so it's just an array of characters. But the only catch with scanf is that that buffer presumably is only going to be of some finite size. And the danger typically with something like scanf, as I tried to demonstrate with some of our programs, is that if you, the user, provide more text than the buffer has room for, what can potentially happen? These buffer overflows, segmentation faults, and therein lies the potential for compromise of systems. And we'll come back to that in our secure coding lecture in a few weeks. Well, it turns out that there are other ways of getting input from the user, some of which are safer fundamentally because they don't trust that there's going to be enough space for the strings. Unfortunately, they require a bit more work because more of the burden is on you, the developer, or in this case, us, the teaching staff. So here is CS50's library's implementation of getString. Notice that it returns a string. It's called getString. We have a few variables up here that we'll use in a moment. And notice that the very first thing I do is initialize some int called size, an unsigned int, to capital size. And again, this is just a convention, but what is capital size probably? Yeah, so it's probably some constant. So let's scroll up, because presumably these things are defined at the top. So at the top of this file, looks like not there. Where else might it be? OK, so if not there, it could be in the header file. And indeed, it looks like size has just been sharp defined to be 128. Somewhat arbitrary. But the idea here is that what we're trying to do with getString is allocate a buffer in advance that's hopefully big enough for the string the user is going to provide. But if not, we're going to grow this buffer dynamically. And therein lies the neat aspect of getString. So what do? We initialize this thing to size. What is this doing in as precise language as you can offer? What's the highlighted line doing? Yeah?
Allocating a segment of memory big enough to hold the size number of characters.
Perfect. Allocating a segment of memory, of contiguous memory, that's big enough to hold size number of characters. We're returning, malloc is going to return what exactly? This is easy. Come on. What does malloc return? Sorry? So the bytes the string takes up, but not precisely, right? Because you can only return one thing. A function can return one thing. So it can't return bytes per se. It can return... Perfect. A pointer to the first element in that chunk of memory, or equivalently, the address of the first byte in that array, in that chunk of memory. All right, we're casting it to a string just to be explicit as to how we're going to treat this, and assigning it to buffer, which is just a string, which is synonymous, recall, with char star. So we could have written this all with char star, but we're trying to use our own synonym for it. Why do I do this? Under what circumstances might malloc actually return null? If it's too big, if you're asking for more memory than, say, the computer has room for or wants to give you. Maybe you're asking for 2 gigabytes, 4 gigabytes, and at some point you're going to hit some limit, and it's going to return null to signify as much. All right, so assuming we do get back a buffer of memory, let's go ahead and do the following. While the following is true, I'm going to do the following. So let's see what's going on here, since we compressed some of this into one line. So f-get-c, as you might guess, is file get character. Where do you want it? What file do you want to get it from? Standard in. So recall that that is sort of a built-in pointer to a file called standard input that just happens to refer effectively to the user's keyboard. So in the past, we've sort of assumed that by just calling printf. But recall, we could have said fprintf standard out, and we could have been more explicit. So that's just saying get a character from standard input, that is the keyboard, so long as that character is not the new line character, and so long as that character is not this special character called EOF, which denotes end of file. The purpose of having that in there is so that you can detect if the user hits Control-D, which is not a typical case, but is more important to have when the user is, for instance, piping content into the program or redirecting it, as you saw you can in problem set 3. So we need that there so that this thing doesn't choke. So now let's just assume that n is not equal to size minus 1. So we're going to go ahead and move down here. So long as n does not equal size minus 1, all I'm going to do is put into the nth location of the buffer the C character. So ideally, if n has been initialized to 0, that's going to drop the first character in the first part of the array. Then the next time we do this, plop the next character, next character, next character, next character. That's it. So it's pretty trivial. But the interesting part is the part I skipped over. Suppose that n, which again was initialized to 0, eventually reaches 127. What's the implication for this process? Yeah, so you need to grow the buffer, because as soon as you've pulled in already 127 or 128 characters, there's no more room to put this thing. So unless you want to just return the string as is, you've got to grow this buffer. Unfortunately, you can't take a chunk of memory and just ask the operating system, can you give me a bit more for this array? I mean, intuitively, why is that probably the case, that you can't just ask the OS to grow the buffer? So it can't. Why might it not be able to store memory contiguously? Like, why can't it just give me more, the bytes that are after the array it already gave me? So they might be in use, right? If I or if some other function also called malloc, by chance it could just happen that the memory right after my buffer is already in use by something else. And yeah, I could touch it. I could just assume I'll take it, but that's dangerous, as we've seen. So intuitively, what are we going to have to do if we want to conceptually grow this buffer? If we can't simply grow it beyond its rightmost boundary, what's an alternative? OK, so we could break it up into 2 pieces, right? Let's just allocate another chunk of size 128 and somehow stitch them together. That might be feasible. What else could we do? Whether you think it's wise or unwise. Yeah? OK, so we could just take this buffer, ask for a bigger buffer, maybe one that's twice as big, and just relocate these characters to the bigger buffer, and then do what with the original? Free. So call free and just say, go use this for whatever else you might need room for. So it turns out the latter approach is what we did with this particular implementation. And it turns out that when you're using arrays, this is really your only option. Stitching things together as you propose is a reasonable idea, and we'll get to this in the context of what are called linked lists today. But when you're using arrays as your data structure, just can't do it. We're going to have to relocate the whole thing in memory. So how do we do this? Well, the moment we've run out of space, and notice that I'm using size minus 1 here so that I'm leaving room for the backslash 0 so that I can fit that thing in there as well. So if the size is greater than this, I seem to be bailing out altogether, freeing up the memory and then returning null. What is that doing? I mean, there's a comment there, but try to translate it into simpler terms. What are these 5 lines of code here doing? So if size is greater than this thing called uint max divided by 2, I mean, you can kind of guess what that thing signifies. U means unsigned, so unsigned int max probably means the biggest possible unsigned int. Why do we care if size is already greater than half that? Yeah?
Because you're about to double it.
Well, if we're about to double it, essentially, we can't double it if we can't represent the larger number given the range of an int. So we have to check for that. If it's that big, frankly, I'm just going to bail, because at that point, we're probably at 2 billion or 4 billion, something like that, in which case the program's getting a little ridiculous anyway. This is not the language we should be using or the data types we should be using in the first place at that point. Otherwise, go ahead and double the size. Then go ahead and malloc just this new size. So that's the same line of code we saw earlier, but I'm assigning it to temp. I'm doing this sanity check. If temp equals null, let's bail out again, because that means there's not enough memory available at this point. Otherwise, I'm using this function. So some of you might have used this already to copy a string character for character. You don't have to do it with a for loop. You can call stir copy, or better, stir ncopy, and specify that you want to copy the contents of buffer up till the \0 into temp, but only do it up to n total characters. And the reason I say that this function's better than just stir copy is simply because it checks the bounds, and it doesn't actually run the risk of doing something bad. Finally, I assign buffer equal to temp after freeing buffer. And what's the net effect of all these lines of code? Well, quite simply, what you proposed. Double the buffer, copy everything over, free up the original, remember the new one, done. Proceed as you were before. So back to this question about a 128. Was that a wise decision for the default value of size? Yes or no? It's a little arbitrary. Sort of the anal retentive me kind of preferred the idea of just declaring it to be 1, starting there, and just doubling it, doubling it, doubling it. Because what's the downside of using 128 from the get-go? What's that? So probably a lot of empty memory. How many times have you guys typed at a blinking prompt more than 128 characters for any of your programs? Not many times. Usually it's been 1 character or a few characters, certainly not 128. But what's the downside potentially of not using 128, but maybe starting with just 1 byte or 2 bytes and then doubling it, but starting from a lower number? Right, so if you do happen to have big input from the user, you're going to have to be calling malloc and free a lot. You're going to be growing and growing and growing the array. So it's not clear that there's a perfect equilibrium in there or a perfect value to choose, which is why I said 128 was arbitrary. But that's ultimately one of these design decisions. And it turns out that memory management, calling malloc and calling free in a C program, typically tends to be very expensive. It can hurt the performance of your program if done a lot. This is going to be particularly germane for problem set 5 when you're tasked with implementing the fastest spell checker possible. And you're going to have to do this for large inputs, files to spell check, and an even larger dictionary of some 100 or 200,000 English words. As soon as you start dealing with numbers like that, if you're constantly allocating and freeing memory just because you didn't make a good judgment call from the beginning of your program, the performance of your program is going to suffer. And so we'll see interesting trade-offs like that in just a week or so's time. Finally, the only lines of code here I've waved my hands at is this stuff at the bottom, which you can look at if curious. But essentially, for efficiency reasons, what we do with getString is once we know that once the user has provided the whole string, and suppose it's a 5-letter word and not a 127-character word, we actually create a new buffer of just size 5, or really 6, move what the user did type into the smaller, tighter buffer, free up the bigger one, and just return the tight buffer to you so that we ourselves are not wasting memory. It costs us something because we ourselves are mallocing and free again, but again, it's a trade-off. So for us, it seemed a reasonable one. Any questions about getString? Okay, we won't look really at get float or get double or any of those in class since they're no more enlightening than, say, get int, but that's about it for CS50's library. I mean, what you've been using now for 5 or 6 weeks is ultimately that kind of code that we simply saved you the trouble of having to deal with from day 1 of the class. So, any questions? All right, so let's come to this suggestion of earlier about like stitching chunks of memory together. So when you've got an array of integers, say something like this, so 9 through 34, suppose I store that in an array. What are some of the upsides of storing data, simply ints, in an array? What's good about an array? Just quick thoughts that come to you. Random access, what does that mean? Could grab any element just by using this bracket notation, or like last week, even using the more arcane pointer notation. What does random access mean? It means you don't have to iterate through the whole array to get to where you want. You just jump there. And that's a powerful thing for efficiency. In terms of big O, what's the running time of getting a specific value from an array accordingly? O of 1, constant time. And that's a good thing, typically. What's another good thing about an array? Anything. You can do binary searches. Because you have random access, an extension of that idea is that you can jump randomly to locations, and so your algorithms can benefit from that, as can binary search. What else? Yeah?
It's easier to initialize all your values. Like if you want 50 different integers, you just type array 50 and have 50 integers sitting there.
OK, good. So it allows you to express sort of larger chunks of data with, rather than defining 50 variables of type int, you can define one variable, essentially, that's an array that contains 50 ints. And I'll push a little harder and say arrays, they're pretty simple, right? Even if you screwed up with them the first few times you played around with them, seg faults and whatnot, at the end of the day, it's not all that complicated a piece of data to actually manipulate. Unfortunately, there's some downsides. So again, consider this to be an array of, what, 5 integers. What's now a downside of representing integers in an array? Potentially. Make any assumptions you want. Yeah? Good. So we've already run into this catch, which is that you need to know in advance how much space you need for this array. Or, worst case, you're going to have to start doing what we did in getString and keep jumping through hoops to make more and more room, which may be acceptable, might not be. What else is tricky about arrays, or bad about arrays, potentially? Yeah?
If you want to delete one of the values, you have to copy everything after it.
Yeah, so what if you so much just want to do something simple, like delete a value from the array? Well, suppose I want to delete 22. Well, how do I do it in an array? I could just change that to 0, but that's misleading, because maybe that just means the array contains 0. I can change it to another sentinel, like -1, but out of context, that might just mean the array stores -1. So what do you do? What could we do? Yeah, so let me merge these responses. Essentially, we could erase it, but if we want the memory to be contiguous and we want things like binary search to continue to operate, we essentially need to shift these elements down. And then we can either just ignore the rightmost element and just decrement the size of this array in some variable, or we can go so far as to just allocate a slightly smaller array, move everything into it, and free the original. That, too, is maybe acceptable. Maybe it's not. What about insertion, just to be clear? So deletion seems to be a bit annoying. What about insertion? What do you do? For an array of size 5, you want to put another int in there. Very reasonable. Right, I mean, it's the getString approach. You're sort of screwed if you've only declared an array of size 5 and you decide, or the user decides, they want to add an additional piece of data to this thing. So there are these trade-offs whereby there are good things and there are bad things. And again, this is this recurring theme when it comes to design decisions. So how can we do better? And I admit the slide we just had up there and the slide you have printed in front of you sort of gives away the answer. But conceptually, see if you can put your finger on what we can introduce here in order to eliminate this downside of insert and delete, at least, being so expensive or being such a pain to handle. I mean, conceptually, what do we want to do to redress those problems? Yes, the answer is singly linked lists, but Yeah, so we want to store where the next chunk of memory is, or to borrow some of the language I used earlier, what if we sort of modify this data structure such that the elements aren't necessarily contiguous, but one sort of does lead you to the next one? In other words, stitch these integers together. Change this data structure so that we have number 9 here, and we have number 17 here, and number 22 here, and 26 here, and finally 34 here. But notice that I've intentionally drawn gaps in between these blocks to suggest that maybe they're contiguous in memory, but maybe not. What I simply need to be able to do is remember that this number, if it's first, is followed by this guy by somehow pointing this guy to this guy, this guy to this guy, this guy to this guy. And this is why all of a sudden this pointer notation, this arrow notation, becomes so much easier than dealing with the OX 1, 2, 3, 4 when you're talking about pointers, right? This arrow literally signifies a pointer, which is to say if I have some kind of data structure that stores 2 pieces of information, one of which is an int, the other of which is a pointer of some sort, it appears that I can model the same idea of a list of numbers, but I can stitch them together in this way, such that there's no assumption that they need fall contiguously in memory. Finally, odds are I want to do something here, right? Because whenever we've had this sort of idea, that's a bad thing. So what do I want to probably store in this structure, if not an actual pointer? Yeah, so null we've seen before is this way of expressing the lack of a valid pointer. So why don't we terminate this list, so to speak, by putting some sentinel there, 0, or rather null. And it turns out if we want to hang on to this list, whereas before we used to refer to arrays by some name, similarly we do that here. And I'm just going to arbitrarily declare some kind of pointer called first, whose sole purpose in life is to point to the first elements of this so-called list. The idea there being I can distinguish between there being a list and there not being a list. In other words, if this pointer is null, how big is the list of numbers? I mean 0. So we have a way of expressing that. So introduce the notion of a singly linked list. And this is the first of more sophisticated data structures, somewhat simple to be sure, but is the building block of a lot of more interesting data structures. And over the course of this week, as you'll see if you flip through this week's slides, we're going to focus a little less on, much less on syntax and new features of C. You've pretty much got the arsenal of skills that you're going to have throughout the rest of the course in terms of syntax and expressiveness of C. And we're actually going to now start using those fundamentals to solve higher level problems. Namely, how do you design software? How do you solve problems in different ways? So let's consider this as the first such instance. This will certainly be relevant to problem set 5, whereby you're going to need to dynamically be able to model a huge dictionary and a huge input file flexibly. So we'll see where this leads us. So we need a way of expressing what these things looks like. We saw last week that piece of syntax called typedef instruct. Well, why don't we deploy that? We need a new sort of data type here, something that has 2 fields. Well, why not express that with this code? So I'm simply going to borrow the syntax from last week and put inside those curly braces the 2 pieces of data I want to keep around. An int, call it n, and then finally a struct underscore node star next. And that's the only weird thing right now. So last week, what we never did in these typedefs was put a word after typedef itself. So our struct for a student last week, recall, said typedef, open squiggly, and then int ID, char star name, char star house, close squiggly, student, semicolon. Unfortunately, this data structure is sort of circularly defined. If this structure needs to have a field that points to another such structure of the same type, we need to be able to refer to it. Unfortunately, the name node or the name student doesn't exist until this semicolon is reached, essentially. So if you want to have this sort of circular definition within a data structure, you need to give it a sort of temporary name while you're typedefing it. Remember that typedef is just a way of providing a synonym for a data type. So if you put after typedef struct, and then the convention among C folks is to put the same data type name prefixed with an underscore, just so it's a little weird but identifiable, then within the data structure itself, can you say, you know what, one of these fields should be a pointer to one of these things. And that's all this is doing. It's allowing us to say that in here is an int and a pointer to one of these things. OK, that's all. So henceforth, each of these little rectangles will be known as a node. So what is the data type of first here exactly, given that definition? if I were to declare first in a line of code, what do I write? What's that? So, n? Not n. So if this thing here. So recall that a moment ago I said I want to be able to hang on to the start of this list by way of a variable called first. How would I define that? It appears to be this square typically means that I'm talking about 32 bits, though I'll just prod you with that. So it's some kind of value. Yeah, so if first is simply pointing to one of these objects, it would simply be declared in code as that. Right? And we saw something like this with our student example, right? Saying something like student star s, I think, or S1 and S2 in last week's example. But the idea is that a linked list henceforth, which conceptually is just a picture like this, the only thing that you need to remember in terms of your code to keep around a linked list is a pointer to the first element in the linked list. Much like to keep around an array, all you need to remember is the name, or equivalently, the address of the first byte. So conceptually, it's the same thing. So if you want to declare a linked list, it's this, quite simply. And better yet, to be clear that this list is initially of size 0, we'd probably in code want to initialize it like that. OK, so what that does initially in memory is it gives you this pointer, but it stores in it null. Not a very interesting data structure, but it is arguably a linked list of size 0. OK, sort of an easy out. But it gets interesting once you start putting things in here. All right, so what can we now do? All right, well, let's go ahead and do this. Let's go ahead and list 1.h. And let's go ahead and do the following. So this thing is going to be typedef to be a struct underscore node. I said that this thing is going to have an int n and then a struct underscore node pointer next. So it seems like I'm calling this field n, to be clear, and this thing next. OK? So after that, I'm just going to say we'll call this thing a node. And that's it. So that's my header file. So that's where I'm putting my data structures. And ignore the dot I'm putting beforehand for today's purposes. So now let's go ahead and do something like this. All right, so here's going to be my program, int main, int argc, char star, argv. All right, I'm going to need to include a few things. We'll probably want to print something, so I'll put standard IO. We're probably going to want to use malloc and free, so I'm going to go ahead and put standard lib, which is where those guys are. And I'm probably going to want to use CS50's library. So I'll use CS50.h. And then I also want to use this file that I myself defined, which is going to be .list1.h. And OK. Good question. So why do I put mine in quotations and these others in angled brackets? I sort of just answered it with the question. Because it's mine, because it's in the current working directory, use quotation marks. If it's built into the system, as are standard IO and standard lib, and also CS50, because we installed that with GCC on nice for you, then it gets the angled brackets. Good. Good question. It is, let's see, it indicates to the compiler where to look for these things. So I believe, I wonder if we can get away with doing this. If it checks, if it just has to do with the default locations. So make list 1. Yeah, so that's the signifier as to where to look. So in this case, it appears that it is required so that you distinguish the two. Other compilers might be more lax, might check everywhere. OK, so here's my first program that uses a linked list. Not terribly interesting. But let's see, what can we do with this thing? All right, so I'm going to very quickly whip up the following. And this is a bit leading since I know where I want to go with this, but you guys will get to give us the interesting aspects of this program, which is namely how to actually insert, how to delete, and how to actually walk on this list. So here we go. Here's my program written up in 60 seconds. So I'm going to give this thing a menu. And I'll put this code online for reference subsequently. All right, I'm going to say if the user wants to delete something from a linked list of numbers, he can just type 1. If he wants to instead find something, he can instead hit 2. If he wants to insert something, he can hit 3. If he wants to traverse, that is walk across the whole list, printing everything out, he can hit 4. And then finally, if he's bored, he can hit 0 to actually quit the program. Okay, so if you've not seen this before, you can actually break up the strings that are going to printf like this line by line. It just concatenates them all together, but it allows me to do things without getting a huge line of code. All right, so now semicolon there. So there's my menu. What do I next want to do? Well, let's ask the user, give me your command. Then let's go ahead and say in C, get the int that the user's typed in so we know what kind of command he wants. And then I'm simply going to switch on whatever command the user has typed. And I'll do these somewhat elegantly with one line. So if he types 1, let's call a function delete, and that's it. If instead he types 2, let's call find and then break. If he types 3, let's call insert and then break. And then finally, if he calls 4, let's call traverse and break. And then finally, while c does not equal 0. So I'm going to sit in this loop again and again and again until the user actually types in the number 0. Whew. OK, so let's see if I made any syntactic errors. Whoops. OK, yes, several. Oh, OK. So good, good. You debug for me. So what's wrong? All right, so I haven't declared anything, right? Because I haven't even gotten around to implementing these things. So all right, so let's fix this real quick. So there's going to be delete function, and there's going to be a find function. There's going to be an insert function, and there's going to be a traverse function, and I don't need that guy. Is that going to fix that? OK. If I'm going too fast, just stop me. What's going on here? Right, so I'm actually now it's a different problem. I did declare them, so we're not getting that same undefined reference. Rather, we're not getting, what was the jargon? Implicit declaration error anymore, which just says, I don't know what these functions are. Now the problem is that down here, I'm actually calling these functions, and they don't yet exist. All right, so now I actually have to implement these things. Let's go ahead and just define this, and I'm really going to punt here and say, all right, that implements that. Find. Not an unreasonable starting point if your goal is simply to make sure that your structure is correct. Void insert. And finally, void traverse. How's that? Implemented? Nice. OK. So let's run this thing. List 1. All right, so now I have a fancy little menu interface. If I call delete, OK, seems to work. Find works, insert works, traverse works, and quit works. So now we have a framework. Unfortunately, we don't really have anything going on in here just yet. The goal of this program is simply to be a little test routine for creating on the fly a linked list of integers. That is, I want this program to let the user, by way of all these different commands, manipulate something that looks like this. All right, so the functions I want to be able to handle are inserting into a list that already exists, deleting from a list that already exists, traversing and printing out a list that already exists, and then just finding a specific element in a list that already exists if that element is indeed there. So how do we do this? Well, what does it take to represent a linked list in memory? In other words, I haven't yet defined any data structures in here. What do I need? How do I declare a linked list? What's that? Typedef? So the typedef declares the data type. How do I declare the actual linked list itself? Over here. So yeah, I mean, this is all it takes, again, to declare a linked list, right? So let's go up here and say that my linked list is really, at the end of the day, just going to be a pointer to a node called first, and by default, it'll be initialized to null. That is to say, at the beginning of this program, there's my linked list. OK, that's reasonable. Right? Now let's see what we can do with this. Now let's imagine, just so we pluck off these functions in perhaps the most conceptually appropriate order, what does it take to actually traverse a list? Well, here's a list. OK, same numbers here. So there I have, in this square at the top left, the variable first, which is, again, a pointer to a node. And then using these using these data structures and these arrows, I seem to have a linked list. And just know that that little aerial antenna thing at the very end there just represents null in some textbooks. So that just represents null, sort of a physical representation. All right, so there's my linked list. What does it take to actually traverse a linked list? That is, if you want to walk from the first element in a list and print out each n within each of its nodes, what do you need to do? Well, actually, let me pull this back down. So here we go. My finger represents first, the linked list itself. What do I need to do to print out the contents of this list? Follow the pointer. All right, so while I'm pointing at a valid node, let's follow this pointer. All right, so here we are. I can go ahead and call printf let's see, quote, %d \n, close quote, comma, whatever I'm pointing at, end field, and we'll see the syntax for that in a moment. Then this guy has a valid next pointer, so I'm going to follow that pointer, print this, follow this, follow this, follow this. Now I see it's null, so I'm going to stop after printing that element. So how can we implement that same idea? Well, let's go back to our code here. Let's actually make traverse a little more interesting now. Assume for the sake of discussion that this thing is already existing in memory. Otherwise, if we're trying to print out this thing, we've pretty much done it already. So suppose that we do actually have this linked list. How do I implement now in code this idea of moving my finger from the first element to the next, to the next, to the next? What kind of construct does that suggest using? OK, so a loop. What do you want to use? For loop. All right, so a for loop. So what do I need to point at each of these elements? So I need sort of a finger. I need a temporary variable to sort of walk through this list. So let's declare that as a node t ptr. And I'm just going to initialize it to null just to be extra safe, though sometimes that might not be necessary. Now in my for loop, what do I want to do? So actually I could, if we want to be really consistent with a for loop, say ptr is going to get initialized to what? How do I start this whole iterative process? Where do I want to point to first? First, right? So pointing here is sort of misleading, because if I set ptr equal to first, what that really means is I'm declaring a pointer called ptr, and I'm pointing it at whatever first is pointing at if I say that. OK? What's the condition that I want to maintain here? I want to do the following while what is true? Yeah, so while pointer is not equal to null. And then on each iteration of this loop, let's come back to this in a second. What do I want to do inside this loop? Well, I want to print out printf, %d, and then comma. What's the syntax here? So pointer is currently pointing at the right node. How do I access its n? So not ampersand and not asterisk. So OK, so I lied. There's one piece of new syntax today. It's the arrow notation. OK? Come on, that's not a big deal of syntax. So ptr is a pointer. If you want to take a pointer that's pointing to a data structure, and you want to grab its datum called n, the syntax quite simply is ptr arrow n. So the reason we're not using star here is that if we simply said star, as we have in the past when we've had pointers to primitives, when you dereference ptr, where you end up is here at this whole chunk of memory. And even though by coincidence it could be the case that star ptr does print out n just because n is the first thing in this structure, the proper way of getting at a specific data member here is to specify it by name. And so that will print out the datum called n in the data structure pointed to by ptr. Yes. OK, good. So equivalent to this, for the curious, is that we could say star ptr, which, to be clear, points me at this data structure. And then, as we did see last week, if you have the data structure accessible to you, then you can simply use dot notation. So know that these are equivalent, but I would argue that the first approach is far more straightforward. But realize that they are, in fact, equivalent. OK? So don't worry if this one looks a bit cryptic to you now. Now let's go back up to this. What's the update? On every iteration of this loop, what do I need to do to physically move my finger to the next node? I can't just do, can I do this? I just spoiled that one. Why can't I do that? So they're not contiguous, right? We could rely on pointer arithmetic there, and hopefully the compiler is going to know how big to increment, how many bytes to move forward. But the catch is these things, though I've drawn them this way, might not be contiguous in memory. Odds are they're not if I'm running this program over time and the memory is getting pulled from different parts of RAM. So I can't just do that, but I can be more explicit. On each iteration, I want to update pointer to equal what? It's next. But I can't just say next because that's out of context. Whose next field do I want to update it to? So pointer's own next field. So once I'm done printing n, I want to move this arrow from pointing to not this node, but whatever next is pointing to. So the line of code that I just wrote has the effect of moving this arrow to be equal to next of this node, which if we look at its arrow is equivalent conceptually to pointing at the next node. All right. Does this code work? It's like 3 lines of code. Does it get the job done? Printing every element in the list. What do you think? You wrote it. I see one head shaking. I hear one person saying yes. I hear an Yeah. Good question. These words first and next, are they part of C? No, they're completely arbitrary. I chose the word first here. I could have called this foo, but first I chose to denote the first element in the list. And next is also just a convention. I could have called this thing anything I wanted to simply by opening up the file and changing what its name is. I could call it the next if I really wanted to. It's just convention. OK, so the guy back here who said yes is correct. This code is fine. So traversing a list is indeed as simple as that. Well, let's take things up a notch now. OK, what's another one that we can do? Insert's kind of scary. How about find? So find's not so bad. Why don't we do this? All right, so the goal here is to take a list like this and actually find an element. And if it's there, print yes or whatever. This can't be that hard, right? Because we've already seen code to do this. Let's do it with a while loop this time, though. All right, again, I'm going to need a pointer. Call it this. I'll initialize it to null initially. All right, then I want to do a while loop of some sort. Actually, why bother with null? Why don't I just initialize it to first, if the goal here, after all, is to iterate over the linked list. And then what do I want to do? While? What do I want my condition here to be, if you know where I'm going? Again, conceptually, I just want to do something while I'm still pointing at something valid. So how do I express that? OK, so while pointer does not equal null. As so long as it doesn't equal null, what do I want to do? And actually, probably help if we ask the user, find what? Right? And then int n get int. OK, so now we actually have something to look for. That's useful. All right, now what do I want to do? So at this point in the story, PTR is pointing at a node. The goal is to see if n equals the value of that node. How do I express that? If OK, if n equals PTR. This is supposed to be more interesting when you provide input rather than me just giving you a printout and saying, here's how you do it, right? So here, if n equals the nth datum in PTR, sure, let's go ahead and print out printf. Yes, we found it. All right, and we're going to assume there's no duplicates, because on Wednesday that'll actually make delete and insert more interesting. So I'm just going to break. Why do I want to break at this point if I found the value, assuming no duplicates? It's a waste of time to just keep iterating if you know you've already found the value. If it doesn't equal that, though, what do we want to do? So we want to update to the next one, so pointer gets pointer next.
Why isn't there a conflict between using n as your
Good question. So why are we allowed to declare n here as a local variable and also call the value within PTR to be n? Someone want to field that? So They're not, so yeah, we can describe it in terms of scope. So in this context here where the blinking cursor is n is a data member inside of structure. And we're being very specific as to which n we want. This n, though, when we just say n outside of any context, is referring to the most locally defined version of n. So quite simply, we're being sufficiently specific as to distinguish the two. So it's not a problem at all, even though they're identically named. All right, so does this do it for find? Yes? No? Yes, thank you. Same guy over there. So yes is in fact correct. Let's go ahead and do the following. And we're going to do this Julia Child style, whereby I run the version I wrote in advance of class. So here we have the menu. All right, so I'm going to traverse the list, and the list is now empty. And I inserted a sleep call just so it would pause for a moment to show us what's in the actual list. All right, so let's go ahead and insert something. What number do you want to insert? 7. Excellent choice. So the list is now 7. Let's confirm as much. Traverse it again. 7. Still 7. What do you want to do next? Let's find 7. OK? So number to find is 7. Yeah, I found 7. Excellent. What do you want to do next? Delete, I heard. What do you want to delete? All right, let's delete 7. Oh, nicely done. So what if we insert 7 again? But what if, and here's a gotcha for Wednesday's discussion, what if I delete like -1? Ideally, that's not going to crash the code, and it doesn't. So you can't make these leaps of faith and just assume that the user is going to give you good input. Let's insert a couple more. Point out that if I insert 10, notice where it ends up. If I insert 2, notice where it ends up. So that, too, is going to throw down a bit of a gauntlet for us, because not only do we need to insert into this list that appears come Wednesday, we're also going to need to sort it simultaneously. Let's go ahead and delete the middle element, 7 being your favorite. It appears we have a nice implementation. So on our agenda for Wednesday will be at least deletion and insertion. Until then, we'll see you in a couple days.